So the next type of circular motion we're going to look at is either conical pendulums or banked corners. So a conical pendulum, if you imagine a pendulum, so a mass on a string, normally we swing it side to side, but you can also spin it around and around in a circle. So this is the sort of a 3D drawing. This is the circular motion of the mass at the bottom here, and this is the string which is attached to the mass. So in this scenario, the mass is going in a circle, which means the equation Fc equals mv squared over r is in play in this situation. But and that means there must be a force on this mass towards the center of the circle, just like in regular circular motion. But in this scenario, this force towards the center, it's a resultant force. It's a resultant of two other forces that are acting. So I'm just going to expand on this, and we're going to draw a force diagram down here, looking at where this centripetal force comes from. So in this scenario, there are two forces acting. Because this object has mass, this object has a weight force on it. The weight force. The other force that's acting here is the tension force. Now tension always acts in the direction of this string. So here's the tension force here, acting up this way here. Okay, so we're going to expand this into a force diagram down here, looking how these two forces add together to give this centripetal force, this unbalanced force. So remember, the way we do this is just to add these two vectors together. So here's the weight force acting downwards, like so. And I'm going to add to that the tension force. So I do that by starting the tension force's tail at the weight force's head and draw it up like so. This is the tension force. Now I knew to draw the tension force this long because the centripetal force is horizontal. Because if the mass is not accelerating upwards into the air or downwards towards the ground, that means that the vertical forces must be balanced. Another way to think about that is that the vertical component of the tension force must be balanced by the weight force, which is acting vertically. So if we add these two together, the total force is from the first tail to the last head. So this is the total, and that is the centripetal force. Okay, so the centripetal force, it's not an actual force, but it is a resultant force of the weight force and the tension force. And the angle in here is this angle, theta. If you spin the mass faster, the angle here is going to increase. The string is going to come out like this, which means that the tension force is going to increase like this, which means the size of the tension force will increase as well. That will cause the centripetal force to increase, providing the extra force required for this velocity to increase. Another example of that is banked corners. So this one's probably going to be a bit more common. If you've been out on the road, or definitely if you go mountain biking, you'll notice that corners often have a bank on them. And the reason for that is to allow cars to go faster, or bikes to go faster around corners. And it's very similar to this over here. So normally if the road was flat, or a mountain bike track was flat, and you had a corner, then all of the centripetal force is provided by the friction force. But banking the corner means that some extra force can add to the centripetal force. So in this scenario, just like over here, there are two forces again acting on the car. There's the weight force acting from the center of mass downwards. And then there is the reaction force, and that's acting on the wheels. So I'm just going to draw it in the middle of the car, acting up like so. And we know that these two forces must give us a centripetal force, a force towards the center of the circle. If the car is going around at a constant height, that means it's not accelerating up the hill or accelerating down the hill. then these two forces must add together to give a horizontal total force, which is the centripetal force. So let's draw this diagram over here. So we have the weight force acting vertically downwards, and we have this reaction force, which is acting up at right angles to the surface of the road or the mountain bike track. And again, I know that these forces must add to give a horizontal total force, which is the centripetal force. Okay, so if I add these two together, here is the total force, which is the centripetal force. And this time it gets a little bit trickier, working out the angle. So the road would be like this, and the angle's in here. I'll just draw that here for you. So this is the road. This is horizontal. Here is the angle theta. So just like up here. The reaction force is at right angles to the surface of the road. It's always at right angles to the surface of the road. And then some maths reason means that this angle in here is theta, the same as the angle of the road down here. Okay, so in both of these scenarios, the centripetal force is the total force on the object, provided by the weight force and one other force. In the case of the conical pendulum, it's the tension force. In the case of a banked corner, it's the reaction force. Because the object, the mass, is not going accelerating upwards or downwards, the centripetal force must be horizontal. Which means if we add these two forces together, the total, which is the centripetal force, is acting only horizontally. And then we can use trigonometry, if we've got the angles, or Pythagoras, if we have the size of these forces, to work out the centripetal force.